Hello dear students, this is Dr. Aisha Nazuk here. Welcome back to my channel. Uh, Today we are going to discuss the topic of hypothesis testing of one population mean. Those of you who have landed first time on this channel called Ravhab, they are advised to watch my earlier videos on statistics and probability theory, especially if you are not very much adept in the concepts of statistics and probability. Then a hypothesis testing topic is maybe not relevant to you, in a sense that you need to first develop the background concepts. Anyhow, for my NUS students, since this is a sequential video, so by the time you are watching this video, you have already developed the relevant concept that you will be able to understand the lecture efficiently. Okay, for this lecture, you can use chapter 10 of the book authored by Douglas Lind. You can see the title of the book and the full author names and all the details on the screen. You can easily download this book from the Genesis library, which is an online resource for downloading books. You are welcome to watch my video on how to download books from the Genesis library, and you can easily download the book from there. So today's topics are relevant to chapter 10 of the book that I've just mentioned. Okay, so let's start from the very basic. What is a hypothesis? The reason I've made a smiley face here is I've used a sort of casual statement here. When a person says that he loves you, generally people don't trust the first time the person says that he or she loves you. But generally speaking, I mean, you need to develop a certain amount of trust before you can, really believe. Nowadays, you can easily understand that people are using this statement even over cyberspace through chats and everything. So I love you is unfortunately sometimes used just a tool for flirting maybe. Anyhow, since the definition of love in itself is so abstract, so if the person says that he or she loves you, that statement may or may not be true. So what is an hypothesis? It's a statement which may or may not be true. So this is a very simple example, and the reason I've used this casual example is, this will help you understand things in a lighter way. So the question is, what is the point or what is the rationale behind the idea of hypothesis testing? Before hypothesis testing, by the way, we covered the topic of confidence interval. So if you haven't, for the time being, if you don't happen to recall the idea of a confidence interval, I would advise that you pause the video here and watch the video on confidence intervals and then come back here. Anyhow, the confidence interval is an approach which offers you a range within which the value of population parameter is believed to lie. For example, if we are given a 95% confidence interval for, let's say, average social intelligence score, we have different dimensions of or different types of intelligence. So for example, in a given population, you want to estimate that what is the average social intelligence score in that population. That population could be, for example, any country. Suppose if we're talking about Denmark, then what's the average social intelligence score there? So let's say the confidence interval says that the score is within the range of 58 and 74. Now the interval is offering you the minimum possible and the maximum possible value of the social intelligence score, in fact the average social intelligence score, but it isn't telling you what exactly is the value of average social intelligence score. For example, if I'm interested to check whether that the average is equal to 68 or not, confidence interval is not directly answering that question. So we do hypothesis testing to take you can say well-grounded decisions whether a parameter equals to a particular value or not. For example, here the parameter is average and the particular value is 68. So as we said, hypothesis is a statement that may or may not be true. So if I technically phrase it, hypothesis is a testable statement. I mean, it's not a vague statement. Whenever in statistics we declare that some hypothesis or some statement as a hypothesis, then it should be testable. In other words, it should not be a vague statement that later on you cannot apply any formula on it to prove it or not. So hypothesis is a testable statement and it is about a population parameter. For example, it may be about population average, it may be about population proportion, or it may be about population variance. So for example, this is a burning issue nowadays, that those of you who are following the international geopolitics, you know that there is tension, in fact a war going on between Russia and Ukraine. So as per my information, Russia's membership of UNHRC is cancelled. So let's say that it was cancelled in April, right? So suppose that before April 2022, Russia wanted to have a rough idea or an estimate that how many countries will vote against it. So suppose Russia had data of 15 countries that in the past have voted against Russia for another such organization membership, right? So the point is, in hypothesis testing we have data of sample and we give results about the population. So for example, if we have data of 15 countries and based on the data of these 15 countries, Russia is going to decide whether the proportion of countries that will vote to suspend Russia's UNHRC membership, whether it's equal to, let's say, 45% or 0.45 or not. So when actual voting happens, this statement may or may not be true. So hypothesis is a testable statement and it can always be tested using data from a random and representative sample. So hypothesis testing. Now we have established that hypothesis is a statement or a testable statement. So what is hypothesis testing? It is actually the procedure of testing the hypothesis. I mean, that sounds too trivial that I'm just rearranging the words in the definition. That's not the case. Just give it a second thought. So hypothesis testing is a full, you can say, step-by-step sequence that we are going to follow to decide whether hypothesis a particular hypothesis is correct or not. By the way, you can see hypothesis testing is applied in a variety of different scenarios. That, for example, I have given one practical application just now when I was discussing about Russia and Ukraine. There are countless other applications. For example, if you want to test that, let's say you have designed a new drug for a disease and you want to see that it's very efficient or it's very effective. So let's say you say that to measure drug efficiency, you calculate, let's say, average number of patients in a given population that are treated successfully. So you can test the average number of people who are treated successfully. Similarly, there are a lot of other applications of hypothesis testing. By the way, whenever a population parameter is unknown, we can always say that hypothesis testing is a relevant decision-making approach. So there are some step-by-step. I'm intentionally going to skip these because in later slides I have mentioned these steps in a much elaborate way. So there are certain steps that we are going to follow while doing the hypothesis testing procedure. So the first step is that we always state the null and the alternate hypothesis. So basically, you can say that whenever we have a statement, we can always have its counter statement or exact opposite statement. So hypotheses are always in pair. One of them is called the null hypothesis and the other is called the alternate hypothesis. So remember that whenever we have equations that have equality signs, for example, equal to, greater than or equal to, or less than or equal to. So all these type of scenarios, they are included always in the null hypothesis, and the exact opposite of null hypothesis is put in the alternate hypothesis. So this is the reason we say that they are mutually exclusive, because by definition they are exact opposite of each other and they cannot be true at a time. So as I said, that whenever we have, you can see that we have three possible scenario. If we have a situation, let's say average, by the way, this Greek symbol mu is used to represent population average, and mu naught is any number. For example, it could be 6 or 10 or any number. So if we have this type of a hypothesis, equal to and not equal to, we call it two-tailed, and you can see equality is put in H naught. Similarly, if we have these type of inequalities, less than or equal to and greater than, then the inequality involving the equal to sign, that's put in H naught. And since the sign of you can see in the alternate hypothesis, the sign is greater than, so we call it upper tail test. And similarly, if the sign in the alternate hypothesis is less than, then we call it lower tail test. Collectively, both upper and lower tail test are also called the one tail test. So before we proceed to step 2, let us discuss that H0 and H1 are also collectively exhaustive. Now what does that mean? Let's say that we want to measure the average IQ in a given country, and let's say based on the past data we know that the minimum IQ in that country is 30 and the maximum IQ is 65. So the set of all possible values of average IQ is between 30 to 65. Now if we want to test that using some sample data, we want to test that the average is equal to 45, then H0, maybe one of the possibility is we define that mu is less than or equal to 45 and H1 as mu is greater than 45. So you can see if I combine H0 and H1, that generates the complete line once again. In other words, it generates back all possible values of the average IQ. So this is the reason we say that H0 and H1 are also collectively exhaustive. Okay, then the second step is to determine the type 1 error, also called the level of significance. So what is type 1 error and why we focus only on it, although we have two types of error, namely type 1 error and type 2 error. So what's a type 1 error? As you can see, type 1 error is when H0 is true but somehow your sample provides such results that you reject it. So it's type 1 error. If H0 is false but you accept it, then it's type 2 error. You can understand this better with the help of an applied example. Let's say your H0 is that the person is innocent and H1 is that the person is guilty. So let's say we are talking about a court trial, and the court has to establish whether the person is innocent or guilty. So let's say if the person is innocent and he is declared guilty, that is H0 is rejected while it was true. So this is type 1 error. On the other hand, if a person is guilty and he is declared innocent, that's another type of error and we call it type 2 error. So that's applied example or applied explanation of type 1 and type 2 error. In hypothesis testing, we focus on type 1 error, or we control only type 1 prediction error, not the type 2 error directly. What does that mean? You see, the formulas that we are using, they are controlling, we are setting the value of type 1 error, but the formulas are designed by the researchers in a manner that type 2 error is in the background already minimized. Once you will see the examples, then you will understand this better, that which formulas am I talking about. For now you can understand that whenever we are doing hypothesis testing, we have to use a formula to decide whether we accept H0 or we reject H0. So that formula, the researcher who designed that formula, they designed in a manner that they minimize the probability of type 2 error. So in the background, type 2 error is already controlled. Type 1 error is in our hand, or we can set its value while doing hypothesis testing. So that's why we always say that we select type 1 error, also denoted by alpha. In the third step, we identify the test statistic, which is in fact the formula that I was referring earlier on. So test statistics is a formula that depends on sample results and the test value, that is the value of parameter in the H0. For example, if you are testing that mu is equal to 6, then the test statistic will depend upon sample results and 6 the test value. So in step 4, we determine that the Decision rule. So as I just introduced the idea of upper, lower and two-tailed tests, so the decision rule for an upper tail test is that we reject H0 if the test statistics is greater than the critical value or the table value. So the critical value is something coming out of a already constructed Z table or T table. In a lower tail test, we reject H0 if the absolute value of the test statistic is greater than the critical value. Similarly, in a two-tail test, we reject the null hypothesis if test statistic is greater than or equal to the table value. So here this is a typo. Reject the null if the absolute. So I should type here right now on screen. Yes, so I'm just I'm saving the slides a bit. So in a two-tailed test, we reject the null if absolute value of test statistic is greater than or equal to the table value or the critical value. So once we do some examples, these decision rules will be further clarified. And in the final step, we take the final decisions. Just for your convenience, I have rewritten the same decision rules here again. So here they are just in the form of a table for your convenience. So let's say we are interested to do hypothesis testing for population mean. Pardon that there is again a typo here, it's not texting, it's testing. So hypothesis testing for population mean when population standard deviation is known. In this case, the test statistics or the formula that we use to take the decision is given by the equation x bar minus mu divided by sigma over square root n, where x bar is the sample mean, mu is the value of population average that we are testing, sigma is the population standard deviation, and n is the sample size. So let's do one example. You can see this is the case. Then we are going to do two-tailed test and under the scenario when population standard deviation is known. So in this question, it's given that the annual turnover rate of 200 count bottle of Bayer aspirin. So Bayer is a brand or a company probably that's offering aspirin bottles, and it follows the turnover follows normal distribution. So what's turnover? It's simply inventory turnover, means that how many times the company has sold out the entire stock and replaced the inventory. So if turnover follows normal distribution with mean 6 and standard deviation 0.5, now let's say that the company thinks that the mean turnover has changed and it is no more equal to 6. So if we use the level of significance or type 1 error equal to 0.05, then what will be our final decision? So of course, if we have the data from sample, only then we can test the hypothesis. So the data from sample says that from the 64 bottles of same aspirin bottles, that is the same data, 200 count bottles, they showed a mean turnover rate of 5.84. So what should we do? Should we reject the hypothesis that the population mean is 6? So let's do the question step by step. In the question you can see that the scenario is only explaining or demanding us to check whether the population mean is equal to 6 or not, right? Because it is just written that it has changed. I mean, they are not suspecting that it has increased or decreased. It is simply talking about change. So we state the null and alternative hypothesis as mu equal to 6 versus mu is not equal to 6. So in the second step, level of significance is already given, which is equal to 0.05, and in parallel we find the table value. So since we are using the Z distribution, so I have attached a screenshot of Z table or the normal table here. So for alpha is equal to 0.05, what you have to do, you subtract 0.05 from 0.5 to get 0.4750. Right? So the table that I am using, it is constructed in a manner that if we have to use it for hypothesis testing, we must subtract alpha divided by 2 from 0.5. And why alpha divided by 2? Because it's a two-tailed test. So alpha divided by 2 is 0.025 and 0.5 minus 0.025 is 0.4750, and we locate 0.4750 inside the normal table, and we can see that the table value is equal to 1.96. So in step 3 we compute the test statistic. So the data we are given that in the sample the mean is equal to 5.84, so x bar is equal to 5.84, and the test value that we were doing test in the hypothesis, as you can see the test value is 6. So mu naught is 6 and sigma is given in the question to be 0.5. If you go back here, standard deviation is equal to 0.5. So, and then the sample size is also again given in the statement equal to 64. So we get the test statistic equal to minus 2.56. Next, the decision rule. As we just mentioned the decision rule towards the start of the presentation or the lecture. So I am rewritten the decision rule. For a two-tailed test, we reject H naught if absolute value of Z is greater than or equal to the table value. Now, the absolute value of test statistic is 2.56, because you can see that we computed it's equal to minus 2.56 actual value, so its absolute is 2.56, because by taking absolute we ignore the sign. So since the absolute value is greater than the tabulated value, so we reject H naught in favor of H1, and we conclude that the mean turnover rate has indeed changed, because we are rejecting H naught. You can see the H naught is mu equal to 6 and we are rejecting it. So we are concluding that the mean turnover rate is no more equal to 6. So next we do example of a one-tailed test. Here we have data of some tires whose manufacturer is claiming that his tires, the tires, if they are used for driving, then the worn out happen by the time at least 80,000 kilometers are covered by that tire, and the standard deviation of the mileage is 8,000 kilometers. So you can see population standard deviation is given, because the data that the manufacturer is providing, it's not out of a random sample. He is making a claim, so that's a population data. Now what happened, that a dealer purchased 48 tires, so that's the name of the dealer, Cross-A Truck Company. They bought 48 tires and they found that the mean mileage is 79,200. Now at 5% level of significance, can we say that the manufacturer claim was wrong, because he claimed that it's going to cover greater than or equal to 80,000 kilometers, but in the sample it has covered only 79,200 kilometers on average. So how to do the test? First step again, to develop the null and alternative hypothesis. So you can see here we have two type of scenarios. At least 80,000 means greater than or equal to 80,000. and its exact opposite is less than 80,000. So I just told that the inequalities or equalities having equal to or involving equal to sign, they are always put in H0. And since we have a less than sign in H1, so this is a left tail test. Okay, so once again, since population standard deviation is known, I am going to use the Z table or the normal table, but it's a one tail test, so I am not going to divide alpha by 2. So what I am going to do, I am directly going to subtract alpha from 0.5 and locate inside the normal table. So the closest possible value that is available is 0.4505, and for this we did that Z value or the table value is 1.65. Next we compute the test statistics. So the data is given that the sample average is 79,200 and the claim value is 80,000, population standard deviation is 8,000 and sample size is 48. You can have a look at the question again and you can easily see that the values I have simply used the information to compute the test statistic, which is equal to 0.693. Next, the decision rule is we reject H0 if the absolute value of the test statistics exceeds the table value, exceeds or it is equal to the table value. So the absolute value of computed Z stat is 0.693 because I am ignoring the sign. So you can see that it is less than 1.65, that is, it is less than the tabulated value. So we cannot reject H0. That is, we do not have enough evidence to claim that the manufacturer is incorrect at 0.05 level. So because we cannot reject H0, so you can see we cannot reject this that the average mileage is greater than or equal to 80,000. So we can say that the manufacturer claim was correct. Now the scenario when population standard deviation is unknown but sample size is large. In such scenario, we simply use the same procedure that we have just followed. The only change that we do that in the formula for Z statistic, we replace sigma with sample standard deviation. Because in large samples, we have this logic that large samples are similar to, or you can say closer enough to the population. So we are going to treat the entire procedure same as we did for the case when standard deviation or the population standard deviation was known. So here I've also discussed if sigma is unknown and sample size is small, in that case we have to switch to another distribution which is called the T distribution. So here we have an example. Suppose that the average annual rainfall for the local area was previously known to be 8 inches. Now a meteorologist believed that there was above average rainfall from 1997 to 2001. So 5 years data. Now the data is given and he wants to test the claim that there was above average rainfall. So if you have these values 8, 5, 7, 5, 6, you can easily calculate the standard deviation and sample mean. So here I've discussed first step on null and alternative hypothesis. You can see that we have two types of scenario, that the average rainfall greater than 8 or it is still less than or equal to 8. So equality sign is put under H0. Next, as the sample size is very small, you can see there are just 5 observations. So sample size is small, so we are bound to use the T test, and I am using the T table against degrees of freedom equal to 4, because for one sample analysis degrees of freedom is always equal to sample size minus 1. So the sample size is 5, so 5 minus 1 is 4, and under the heading of one tail we choose 0.05 because you can see that this is a one tail testing procedure. Two tail means equal not equal, so but this is not that scenario, it's a one tail test. So under one tail we pick 0.05 and the degrees of freedom 4 and the value comes out to be 2.132. So we compute the test statistic. As I said, that you simply calculate the sample mean and sample standard deviation. So you can verify easily, these are just 5 values, you can easily calculate it, their mean and standard deviation. So the sample mean is 6.2, sample standard deviation is 1.3 and sample size is 5. So T statistic is equal to minus 3.10 if you simply switch the values. See, this is x bar minus test value of mu divided by sample standard deviation over square root of the sample size. So the decision rule, as it's a one-tailed test, and you can see which type of one-tailed test it is, mu is greater than, so it's a right-tailed test. So I just mentioned, in the right-tailed test we reject the null if test statistic exceeds or equals the table value. So here the table value is 2.132. So the final decision is that the calculated value is equal to minus 3.10. Pardon, I have again written here plus, so this is minus 3.10. So the value of T calculated is minus 3.10 and it is not greater than the table value. So we accept the null hypothesis that average rainfall is less than or equal to 8 inches. So that was another example. Next we do an example when the data is large or the sample is large and sigma is unknown. So this time I've used a different type of a confidence level. So sample size 200, sample mean is 35 and standard deviation is 10. We test the hypothesis that population mean is 30 at 99.99 level of confidence. So if 99.99 is the level of confidence, then 100 minus 99.99 will be type 1 error or level of significance. So the null hypothesis is simply equal to 30, not equal to 30. Rest I've just, this is not the part of the hypothesis, I've just written here as a part of a data. Sample size is 200, x bar or the sample mean is 35, sample standard deviation is 10. So these are all given in the question. Test statistic is still Z. Why is it Z? Because the sample size is large enough. It is much greater than 30, you can say. So if in a large sample I can still use the Z distribution, and by in the denominator you can see I've used S instead of sigma. So this is the value of Z statistic coming out of this sample equal to 7.07. So the rejection rule, once again we are talking about a two-tailed test. So rejection rule is if absolute value of Z exceeds or equal the table value of Z. Now as I said that confidence level is 99.99, so alpha is equal to 1 minus 0.9999, which comes out to be 0.0001. So we subtract it from 0.5 to get 0.499, and 0.499, as you can see, it occurs against the value of Z, which is 3.9. So the absolute value of Z calculated is greater than the Z-tabulated, that is 3.9. So we reject null hypothesis. So I think these examples, they must have helped you understand the general procedure of hypothesis testing, some applied calculations as well. So if you want to further do some practices for my NUS student, I have uploaded a practice activity on the learning management portal that we call here in NUS as LMS. Apart from that, even the general viewers, they can go and refer to the solved examples of chapter 10 of Douglas Lind book. And if you are very enthusiastic to try other type of challenging exercises, you can refer to the chapter exercises. And the good part is that the answers are given towards the end of the book. So you, as I said in the beginning, you can download the book from the Genesis library. So thank you for watching, and I hope that this lecture videos help you understand the important concepts, and I wish you best of luck for whichever purpose you have watched the video. In the end, a humble request to please subscribe and share the videos in your social circle, so that will be you can say your way of showing gratitude, probably, as you see that professors put in so much of effort in sharing knowledge. So, and I believe that knowledge is a public resource. I don't believe in putting knowledge under constraints. So you're more than welcome to share these lecture slides, lecture video with others. If you are interested to get these PowerPoint slides, you can always put your email in the comment section, and I will reach out to you, or I'll shortly also mention my email in the comment section of the video, so you can drop me an email. Thank you, and I hope to see you in the next lecture video.